After an exciting talk from the finance industry, welcome back to track 4. We have one highlight after the next. So right now we dive into industrial vision applications. Who does not know the issue of noisy labels, partial missing labels? You start to develop your application in lab environment, everything is fine. You go to the industrial application, to the machine, and you start to having serious problems. Welcome on stage, Nicolas Simmler, Pascal Sager. So, Pascal Sager is studying data science at the Zurich University of Applied Science. At the same time, he works at the university-founded Center for Artificial Intelligence. Nicolas Simmler is currently closing the master's degree in applied informatics and data science in Lucerne, so locally. And he works part-time as a forensic data analytics consultant at PwC. So, warm welcome. I'm very curious to see all your insights about industrial vision. The floor is yours.
Perfect. Thanks a lot for the introduction. We had a small paper with this beautiful title that you can see here. We surveyed different learning methods that you can use when you have potentially issues when you apply them in a real-world project. So who are we? As you can see, Pascal and I here on the stage. There are a couple of more people here, even here at the conference, that helped with us. Basically, we unified two different perspectives that dealt with the same issues. There's, for one, Pascal's team, who had one look from one perspective, and me, which wrote my master's thesis on this topic. What are we going to talk about in this short period of time? Quickly, I'll clarify some terminology that you might still be confused at after reading the title. Then we'll talk about why these issues might happen. Then we'll give you the core part, some methods we found that could help you with dealing with such issues. And then Pascal will take over for discussions. And then we have time for some questions. So just to set some ground terminology here. There are different. We had as I said, two different perspectives coming into this paper. One is the classification part, and then there's the semantic segmentation part. For those of you who attended this morning's automated driving talk, you already know about semantic segmentation, which is the part of detecting areas in an image which represent an object. And the classification part basically lets a model classify an object, what it is actually. Like here, for this horse that you can see here, you want to have the horse, right, as an output. So what are missing, noisy, and partial labels? We tried to illustrate this here with this slide here. Imagine you have an image of sheep and a dog, right? In a scientific, perfectly labeled lab environment, you would probably get a data set that something like on the bottom left. You will get labels for the classification task. They will tell you there's a dog and there's sheep. In the semantic segmentation part, you would get like segmentation masks, pixel level annotated, nice masks, right? If you have noisy labels, that means that one sample or all the samples of a class or multiple classes are confused. So there could be, in that case here, that dog label might be a cat, right? But not all of the dogs would be a cat. Just some stuff is off. The same for the segmentation masks, right? It could be that this mask that you get could mean that it's a cat then, or like an airplane or whatever. The missing labels, as the name says, parts of the labels of the objects in that image are missing, right? In our case, you would only get the label for the sheeps in this case. The same goes for the segmentation masks. The partial labels only apply to the semantic segmentation part. That's interesting, especially for the industry, because sometimes you don't have pixel level accuracy, right? So in that case, hand annotations, or as in this case, where you only have a line denoting there is an object of this kind, that's something that might be interesting. Not just from the perspective of, as an issue, but also to maybe save some money, right, in your project. I'll get to that in a second. So what are some root causes? Like for the noisy labels, for instance, a typical root cause is when you have in an industry project multiple experts labeling, for instance, your data, and then they disagree on the label, right? So that could be an issue right there. And another thing is you could have missing label if the people are not careful enough, then because they are stressed, they need to meet the deadline, right? So if you have no quality checks in the end, then you could end up with these issues. And then there's just like the typical errors, human errors, right? After labeling 1,000 dog images, it could be that some of them are wrong, right? That they might have mistaken a cat for a dog. So what's the issue? Like how does that look like when you have such data set? Like during my master's thesis, I had to look at these issues particularly, and I saw these curve quite a lot. In the case of noisy labels, if you have noise in your data set, the performance of your network, which you see here on the y-axis, after a while, the network will not be able to learn a certain degree. This curve originates from a binary classification task where you have to predict either true or false for something. And after a while, the network just doesn't know the model what to learn, right? Ideally, we could have a network that works like this. It basically just ignores, or can still learn and ignores it, right? That would be really cool. But we would also be happy sometimes to just allow some noise and to still work. So how can we solve these issues, right? Obviously, the easy one would be easy. The obvious one is to just make sure the data set is clean. But for obvious reasons, like cost reasons, most of the time in the industry, you can't do that. So we would need some methods to solve it on the model side, right? That allows us a couple of things. For instance, the most interesting one is we could save costs. Like if people just need to label, with like 80% accuracy, or confidence, then they can be a lot quicker. The same goes for the partial labels, for instance. It's a lot easier to just scribble on an image than to make pixel level annotations. So we found a couple of methods to do that. In that case, for the noisy labels, one of the current state-of-the-art methods that looks really promising is called divide mix. This image looks a bit daunting, so bear with me. The most interesting part happens at this area here, and this whole image basically depicts what happens after each training epoch. So what happens there in this mixture model that's there? Imagine if you have two images of a dog. One is labeled as a dog, and the other one is labeled as a cat. A network who knows how to classify dogs will not make an error on the image that is labeled as a dog, and make an error that is labeled as a cat, for instance, right? And if you do that for all the images in your data set, you can get distributions of those error values. So they use the error values, like the loss values, and try to model those. And then once you get this nice distribution here, you can then do something with it, right? From the noisy case, for instance, in divide mix, they will use, as you saw here, two networks trained simultaneously. They use the other network to predict the labels of the other one. And in my master's thesis, I had a different approach, but still looked at the same principle, basically. Another method that's really interesting is called sharpness-aware minimization. And that's actually a really interesting one. I'll get to that in a second. The cool thing here is it not just tries to optimize during training, right? But it tries to optimize in the loss landscape to flatter areas. That means if you have a little different input, it would still predict, it's still generalized quite well. You can see this on the right image here. If the testing function for a sharp minima is a bit off, you will be completely off in the prediction. And if you have a flat minima, then that means you're still somewhere in the right area. The reason why I'm showing you this is actually this one. It's really easy to implement and also really interesting for the industry because of that. And I saw it in my master's thesis that it works quite well. Here is, you see, the implementation is basically one line, right? You wrap your optimizer, and then you do the normal training. You can use any optimizer. The downside of this method is it uses 2 full passes through the network, backwards and forwards. So that makes the training a little bit slower, but that's due to the fact how that stuff gets calculated. So, but it's really simple to implement, and it works really astonishingly well. Then, for the missing labels, we found that the typical, like all people, whenever they talk about missing label, they talk about label propagation. Obviously, you can use something like divide mix that we just saw to predict the other network's label, but typically, label propagation is the way to go, right? And as you can see here in this image, it's an iterative process normally. That doesn't make it that easy to implement in a neural network, but yeah. Then there are networks like this transductive propagation networks who does exactly that, right? It does end-to-end, gets your data, does the graph construction, and uses a similarity matrix to propagate the labels in that graph, right? So that means we can apply label propagation using deep learning. We can learn it, and it works. Yeah, and with that said, I would like to hand over to Pascal.
Thank you. So another approach to tackle this issue of missing labels is called contrastive learning. So here you can see the SimCLR framework, which is a pretty well-known framework in this area and representative for a lot of contrastive learning approaches. So the main idea is that we take an image, and then we augment this image twice, so we get 2 augmented views of the same image. And since it is the same image, we know that these 2 augmented views, that they have also the same label. And then basically the goal of contrastive learning is to extract good feature representation of this image, and this is done by this encoder. So we feed these augmented views through the encoder and end up with some representation vectors. And afterwards, to update the parameters of this encoder network, we use a small projection head to map them into the space where we then can apply the loss function. So that the main idea is that we augment this image twice and then to maximize the similarity between these 2 views. And we do this, for example, for the images of the cats and also for the images of the dogs and for all other classes. And in the end, we are able to calculate pretty good hidden representation vectors. And the interesting thing about this is that this works without any labels at all. And afterwards, we can use these hidden representation vectors for some downstream tasks. So for example, we can combine these images with a small amount of labeled data and then do normal image classification. So, so far we talked about noisy labels and missing labels. So the last part of our presentation is about partially labeled data. So this is only interesting for semantic segmentation, where the goal is to predict basically a label per pixel. So we don't want to predict a label per image, but per pixel as it's shown down here. And one issue with this approach is that generating these pixel-level annotations is really, really time-consuming and therefore also expensive. So it's much cheaper to use, for example, bounding box labels or image-level labels. A pretty simple approach was presented by Ye et al., and this one is shown here, and they just used all types of annotation by using an annotation-specific loss function. So what they did is they took the image, they fed it through a convolutional neural network, so there could be any type of network, which outputs a feature map. And then if they had the pixel-level annotations available, they used the pixel-level loss. If they only had the bounding boxes, they used the bounding-level box, and otherwise they used an image-level loss. And what they found is that all 3 types of annotations, they really helped to improve the network. So that means that not always necessarily we need to have the pixel-level annotations, but we also could optimize an image for semantic segmentation, for example, using bounding boxes or only image-level annotations. So another really interesting approach is this one here, and this one shows that we also can do semantic segmentation only with image-level labels. So, and this works as follows. So first we train a classification network, which is able to classify the image on image level. And then we have a look at the class activation map. So the class activation map is just a visualization where the network puts the attention. So if it wants to classify this image as a couch, it has to look at the center of the image because the couch is there, and then it can classify it as a couch. And the idea is to use this class activation map like as a localizer where in the image the couch is. So we know it's somewhere here in the center, and then to expand this area to the object boundaries. And by doing so, we can basically calculate from an image level label the pixel level labels and use the pixel level labels for the semantic segmentation task. So we presented you 2 approaches each for noisy labels, missing labels, and also for partially labeled data. Of course, there exist a lot of more approaches, which we described in our survey paper. So if you are interested in it, you should definitely have a look at our paper. And we also think that a lot of the models are still evaluated on the well-known benchmarks, such as ImageNet. And that does not necessarily mean that they always are useful, for example, for real-world data sets. And therefore, we think it would be necessary also for the research to have a shift towards more real-world benchmarks, so also evaluating them on noisy data sets and not only on the clean ones. We found that these 3 issues are pretty well addressed in today's literature. And yeah, we also think that allowing some noise in the data could pay off. So it's often the case that you, during data collection, not really aware that you're also collecting noise, but afterwards, when you implement the model, you see that the data is not that clean as you thought, and then it could be, or it could pay off, to just use a model which can handle this noise instead of relabel all the data. And last but not least, we also found that there exist a lot of good models how we can do semantic segmentation without pixel level annotations, and especially from the viewpoint that pixel annotations are that expensive to acquire, there could be really interesting approaches for the industry. So thanks a lot. And
thank you very much. The applause is for you. A little present.
Thank you.
Very nice insights in the industrial vision. Now it's time for question. I'm still waiting for the first question from the people in front of the screen at home. And in the meantime, questions here, or I can, of course, start. So what do you think is your maturity level to jump from the lab to a real application? Did you test these approaches already on real data, or is it like test sets from challenges?
Yeah, it has to be said, like this paper preceded basically my master's thesis, where here we looked at different approaches, what they could do, and in my thesis I basically actually evaluated them and made sure that I tried to figure out which ones work well. And as, for instance, the sharpness of error minimization, which I briefly presented, worked really well on real-world data that I saw, which makes it really interesting because it's easy to implement and works well. Obviously, with the drawback that the training might take a little longer, but not crazy much longer. So some of them really work, but I also found that other methods don't work, even though they seem to score really well, as you said, on scientific benchmarks. Why that is, it might just be because sometimes people try to just achieve high scores in everything, and without regards to whether it actually works in other areas.
Would you expect in a real industrial use case a mixture of all these things? So you will have noisy and partial missing and loss and lost labels, so you can combine all these technologies?
Yeah, I mean, it's not that easy to I mean, if you want to get a 100% clean data set, it's not that easy to get it perfect, right? Even for some of you, it might be the name ImageNet is a name, right? That's one of the biggest data sets out there, and where everything gets benchmarked on. And even there, a recent paper showed that there are a couple of issues in there, label noise. Surprisingly, sometimes an obvious class like a horse gets mislabeled as a dog in there. I mean, if you're interested, have a look at labelerrors.com or so. It's surprising how many issues there are even in scientific standards.
We have one last question from the audience. Just stand up. The microphone is sensitive.
I was wondering, have you considered that the labeling itself is a classification or assignment problem by itself? In a real-world scenario, we don't necessarily know what kind of labeling error we have. So per se, we don't know what kind of method we want to apply. So that actually is a meta problem you should solve beforehand. Have you considered that?
Yeah, I mean, we didn't consider it directly in our paper, but obviously just to figure out that there is an issue with your labels, that's already a really hard task. People think like, yeah, we are always 100% correct when we work, but like everybody makes mistakes, right? So it's not that easy to figure that out.
Okay.
Thank you very much, Niklas, Pascal. Thank you very much. All the best.